Hello, and welcome to Donaldson's Clean Fuel and Lubricant Solutions webinar, Winterizing Your Diesel Tank and Fleet. My name is Jim Doyle. I'm an engineer in the Clean Fuel and Lubricant Solutions group here at Donaldson. The objectives for the presentation today are to discuss tank behavior and issues critical to winter fuel storage, discuss diesel equipment tank care for winter operation, successful winter operation, and to discuss critical fuel parameters for trouble-free winter operation. Winter conditions can be hard. On equipment, you can have heavy engine oil, in this case 15W40 at minus 20 degrees Fahrenheit. As you can see here, it isn't really flowing, it's a solid. You have cold oil at those temperatures. You may be using block heaters, blanket heaters, etc. to even get equipment in a temperature range where it can begin to move. Fuel can also have issues. Here's an example of a dispenser filter that isn't going to be allowing much fuel to flow. You have water and fuel solids forming a complete solid, essentially plugging the filter, and that can lead to difficulties to getting equipment operating. I'd like to talk a little bit about storage tanks as winter sets in. From the outside, a typical storage tank, in this case a 500-gallon horizontal above-ground fuel tank, pretty much looks the same summer and winter. It looks pretty standard on the outside, but there's an awful lot going on inside that tank that you can't see, that changes as temperatures go from fall into winter, and again from winter back into spring, and on a daily basis. In the winter, generally people think things are dry. There isn't much moisture around. It's not the amount of water that's around. It has more to do with temperature changes between the fuel, the air, the headspace in the tank walls, that causes water conditions, water generation conditions, and adds water to your fuel tank. This is a fairly complex graph. I'd like to take some time to step through here to explain what's going on inside that tank that seems to look from the outside the same all year long. If we look first at the light blue line that start over on the left, you'll see that axis is labeled headspace temperature. There's a temperature sensor in the headspace of an above-ground fuel storage tank in central Iowa, in this case from October into January several years ago. You can see the blue line moves up and down daily, but generally trends down to winter conditions. It starts out roughly around 55 degrees Fahrenheit there on the left in early October or mid-October, and as you head towards January, you can see it settles in around about 15 degrees Fahrenheit with daily spikes up and down. Not unexpected, that's exposed to the atmosphere essentially. Above the top, across the top of this diagram is a red line, and that happens to be the headspace relative humidity. You'll see the right side shows the relative humidity on this graph, and you'll notice through that same time period, the relative humidity in that headspace is very, very high. Much of the time it's spiked at 100%, probably at least 30% of the time, and probably 80% of the time it's above 90% relative humidity in that headspace. So there's definitely moisture there. You can see when the conditions warm up in November in the headspace temperature goes up, the relative humidity in the headspace goes down because air has an ability to hold more moisture at that point. But what's going on here is a interaction between the fuel that generally stays at one temperature or moves very slowly, and then daily as the sun comes out and the sun goes down, the headspace is changing temperature much quicker than the fuel, and it creates a condition where the cold tank wall that's exposed to the outside atmosphere can have condensation going on it because of that headspace relative humidity and the even colder tank wall. So that the exposed tank wall at the top of the tank is where all this condensation is going on. It's not water absorbing into the fuel, it is condensation occurring on the inside of that tank that is generating the water in the tank. Consider, if you will, a beverage out of your refrigerator in the summer. If you take a beverage out of your refrigerator at 38 to 40 degrees Fahrenheit and set it outside on an 85 or 90 degree day, almost instantly you have moisture condensing on that cold surface. If you take that same beverage out of a tank and it's out of a refrigerator and set it outside on a 40-degree day, you won't have any condensation occur on that can at all on the outside. There is no temperature differential to really get any condensation going and start generating moisture on that surface. So the can surface will stay dry. The same thing is going on here, it just is on the inside of the tank. So again, the tank looks pretty much the same all the time. In certain conditions, you can see condensation on the outside of the tank where the fuel is, but this condition is going on, as you see in that graph, almost all the time in that fuel tank. Even in the winter, you'll see it spiked near 100% relative humidity. If you take the cap off of one of these tanks in the winter, you'll actually see moisture there on the inside of the fill cap on this tank. That's icicles frozen on the underside of the fuel tank. Further evidence to show that that water is condensed on the inside of that tank surface and just continually collecting water there that when it warms up melts and runs to the bottom of the fuel tank. So those temperature changes are critical to generating this condition to produce moisture that collects in tanks. And on vehicle, that can be even further exaggerated. Many modern engines fuel systems return hot fuel back to the tank. And when you start a vehicle with a full tank of fuel, you begin burning that fuel and returning some of that warm fuel back to the storage tank. That's just a function of how high pressure common rail fuel systems work. And you're warming that fuel with the tank sitting in cold conditions. So the headspace of that tank that's exposed is going to be much cooler than the fuel itself in the bottom of the tank. And as you consume that fuel and have more and more headspace in the tank, the fuel is warm and you have more exposed headspace of the tank that can allow condensation to occur and collect moisture that will run down and be mixed into the fuel in the fuel system. Methods to avoid this include a common adage that's been around for years that you should top up your tanks at the end of the day, and consider that if the tank is low and you've been producing a little bit of moisture, if you fill that tank up with fuel so there isn't any headspace left, there's nowhere for condensation to occur or much less surface, and you'll generate less moisture in your tank as the fuel is sitting there warm once you shut the vehicle off, and you'll minimize the amount of water buildup in the bottom of that fuel tank. Not that water isn't going to be produced as you're driving around with that temperature differential, but anything you can do to minimize the amount of time you have some warm fuel and a lot of headspace in the tank will help you avoid faster water buildup in your tank. So you are going to have water building up in your tank system. It's a challenge to prevent all condensation from occurring. And what can you do to prepare for this or counteract this as you transition from fall into winter and perhaps during the winter depending upon conditions? Here's another typical 500-gallon outdoor storage tank. If there's a little bit of water in the bottom of this tank, you may be able to get a hose to the bottom of the tank, the dead bottom of the tank. Most tanks don't have a dead bottom drain. Some mobile fueling equipment does. Perhaps some gravity drain fuel tanks do, but most have the ability to collect some moisture in the bottom, and it's difficult to get at. In this case, a hose that is put down at the bottom of the tank on the low end can get some moisture out of there, and you can perhaps get it out of there and collect it in an absorber filter in this circulation system and get that fuel clean and dry prior to winter. If that water has frozen in the bottom of the tank, that's probably going to have to stay there until things warm up. If you're operating a system that has a pump draining near the bottom, you do not want that water building up, or it's likely to plug the pickup from your tank, whether it's a stationary tank or a mobile tank. If the fuel pickup is near the bottom and you have a significant amount of water there, you can freeze ice on that pickup, and you will not be able to get that going until you can thaw that out. So touched on here in a few different ways is the concept of preparing for this situation in winter and making sure you do everything you can to limit things that can happen to stop you in your tracks in the winter. And the key to that is isolation of your fuel. Filtering on delivery, whether into a bulk tank or a mobile tank or a piece of equipment, to prevent additional particulate and water from getting into the system in the first place, once you've cleaned it out in the fall, is the best practice. If you can do something to isolate that fuel with a breather to prevent particulate from getting in, but even more importantly, potentially moisture, The possibility, if it exists, if you have a dry air source, you can purge the top of that tank reservoir and prevent any moisture from collecting on that headspace and draining down into your fuel, and keeping your fuel nice and dry. It will have the best chance to be usable when you need to use it in the winter. And then just filtration on the way out to make sure you're not transferring any issues in your fuel storage tank onto your equipment. Perhaps water that is condensed and the pump picks it up. You could absorb it on the way out. So winter fuel and storage and water bottoms, we've kind of touched on a little bit. They can cause some significant hazards depending upon the system they're in. This is an example of two samples of fuel that have water in them, obviously, or had water in them. The sample bottle on the left was emulsified. The water was fully scrambled up into the fuel when these were set to cool, and the other had water just simply sitting at the bottom. You can see all the water has been driven out of the fuel. It froze, it settled to the bottom and froze very, very easily. These are in minus 20 F conditions. So they look very similar here. And the solids at the bottom, the ice obviously is going to plug dead bottom drain valves coming out of rail cars or fuel trucks that are a gravity drain. They can be ice that can settle in there. It can freeze around the pickup of a dispenser pump. You want to limit that to be able to actually pump the fuel that's supposed to be liquid. Here's another actual tank bottom sample, not a made up one like those in the small bottle, but this is a tank bottom sample from the middle of the winter. You can see that diagonal chunk of ice in there as this bottle sat over on its side out in cold conditions. There's some solids and a little bit of fuel left in the bottom there. That the fuel is still liquid. The ice is obviously frozen, and the dirt that settled into the bottom of that tank is still there as well. All that together can make a real problem for transferring fuel out of this tank. Winter fuel and storage tanks can create other solids as well, and in this case, the example that I showed earlier with the small bottles of fuel with the water frozen at the bottom were allowed to thaw out. These were a B5 5% biodiesel blend with water added and then cooled off. And you can see in this instance some solids had formed at the interface of the fuel and the water. This was the emulsified sample. The water and fuel were in close proximity before settling out and freezing, and some additional glycerin dropped out of the biodiesel and formed solids that settled at the interface between the fuel and the water in this case. That will, if picked up by a pump, will transfer even when things have warmed up and can plug filters, load on filters and plug things up. So solids generation, not just from ice forming, but also the fuel may create some solids as well in those conditions if there's additional water present. And that's another reason to keep water from collecting in your tanks, or get it out of there at the end of the summer or early in fall, to make sure you don't have this additional particulate generation going on. Winter fuel in storage tanks can also turn hard, as shown earlier. Here's an example of 3 samples of fuel from one site using a straight number 1 in the winter on the left there. That is a fuel that has is designed for use in winter. It is a liquid at cold temperatures. This happens to be 10 below 0. You can see right through it. It's clear. It's still all liquid. The center and right samples are number 2 off-road and number 2 on-road fuel, and you can see they're both completely cloudy. They are below what's called their cloud point. We'll get into more of that in a minute. But you can see also above in the headspace in those sample bottles, particulate on the walls of the plastic bottle there, and that is solids in the fuel. Gelling in fuel is a massive increase in particulate formation. Far larger percentage of the fuel turning to particles than the filters are designed to remove hard particles. Fuel at normal contamination levels maybe has 1 ppm of hard particles in it that filters are designed to remove as you operate equipment. When fuel gels, you have significant percentages, 5, 10, 15, 20% of the fuel turning to solids. That is a lot more particles than the filter can handle, and that's why things plug very quickly in winter. Uh, Gelled fuel solids have a certain look to them, and as I mentioned, a certain percentage can turn to solids. The further you go below cloud point, the higher percentage of the fuel turns to solids. In this case, this is a southern U.S. summer fuel at 20 below zero Fahrenheit, and almost the entire sample has turned to solids. There's very little liquid left in this bottle, and nothing is going to operate on this. You're going to have to use a fuel that's designed specifically for your conditions, and that's where we want to get into fuel properties and what's important. So here's what waxes look like in fuel. Traditional high sulfur fuels formed plate-like or flakes of wax, roughly 100 microns, perhaps even larger, and those could float around in the fuel and get picked up, and they can plug screens and pumps and load on filters very, very quickly. You can see these are 100 microns in size, and they're going to plug just about anything, even coarse filtration and screens. In cold conditions with more modern fuels, this is an ultra-low sulfur diesel blend or biodiesel blends. You'll get a crystal that's more of a, it looks more like a spiny sea urchin. You can see 2 or 3 of them there circled. They have a central core and then spikes coming off of them. And you'll notice there's a 20 micron scale bar in this image. Those are much smaller particles. They're less than 20 microns. So they can move through screens and perhaps coarse filters a bit. You're still talking a large percentage of the fuel has turned to solids and can load on things. But these are with cold flow improver in here, form this type of crystal and stay suspended a bit more. It'll help move fuels around. For modern engines, particles of this size are still going to be filtered out at nearly 100% efficiency or more, and you're going to start plugging filters quickly. So some critical fuel parameters and different additives people use in the winter are also can be beneficial or cause some headaches in operation. A very common one mentioned briefly there was cold flow improver is added into fuel, and it helps fuel flow. It does not help it become filterable or keep the fuel liquid at a colder temperature. I showed fuels there that are liquid at cold temperature next to fuels that are not liquid and are forming solids, and the cloud point with cold flow improver does not change. Only blending number 1 and number 2 diesel, naturally changing the cloud point, changes the temperature at which solids start to form. We saw an oil sample and another fuel sample in this presentation that were colder than their pour point. And you saw that initial engine oil sample that was still completely solid in a bottle. You're not going to filter that. It's not going to flow. You're not going to start an engine on something that's that thick. And that there was a fuel sample that was similar. The pour point isn't really something critical to actually operating a piece of equipment on fuel. A huge percentage of the fuel has turned to solids, and the fuel is well beyond a usable point. You need to be trying to run your equipment at a temperature above the cloud point. That's the temperature which you can visually start to see particles form. 5 or 7 degrees above that is when waxes start to form in the fuel, and you'll start loading filters quicker than expected and can start to see operability issues. So the most critical number to know is the cloud point, and you always want to be buying fuel that you expect to be running at a temperature significantly above the cloud point. Several degrees above the cloud point would be best. We've talked a lot about water here in the winter, and that it tends to collect in fuel in the fall and into winter. It does the rest of the season as well, but it can cause even more headaches as it freezes and turns to solids. So there's a couple of additive families that are used in fuels to try and change what's going on with water. A common one in marine applications and some others is called an emulsifier. And that additive is put in the fuel to try and get the fuel to carry more water out with the fuel. So the water will stay in the fuel and be carried out of your storage tank and or into your engine tank and move on through the system and not collect in the bottom of your tank as much. That decreases the efficiency of your fuel water separation technology generally, but it is a way to keep water from collecting in your tank and freezing in the low points and plugging up your fuel pickup, that kind of thing. There's another type of additive used in fuel called a demulsifier, and it does the opposite. It freezes it forces water out of the fuel to the bottom of the storage tank so that the fuel stays dry and clear and can be moved. Both are employed in different situations, and you'll see them both seasonally in different situations. Also to consider, I showed a little bit of example of some solids generation with a biodiesel blend that had been frozen in the presence of water and then creating some additional solids. In Canada, for instance, North America, they avoid biodiesel blends in the winter almost entirely. In the United States, northern tier states most avoid biodiesel blends, but not all. There is biodiesel used in winter in northern states. It's more common for biodiesel blends to be prevalent year-round in the southern U.S., but even there it tails off some in the winter, and it's because of that additional contribution to solids generation. If you can avoid biodiesel blended fuel, if you can, in the winter, it's best advised. Regulation-wise, you may not be able to avoid it for many states. It's just a fact of the standards. One other fluid that's not diesel fuel related here, but's critical to consider this time of year in the winter, is diesel exhaust fluid. That is a ultra pure water and urea mixture for dosing into your exhaust system, obviously, and it is liable to freeze when temperatures are below freezing. Storage systems for those generally keep it above freezing, and the filter and the dispenser system and everything needs to be kept above freezing to stay liquid. That can be an issue in northern situations, but it's just another winter issue to keep in mind. That concludes the presentation today, but there were a couple of good questions that came in for this presentation from participants, and I thought I'd cover at least one of them because it's critical to many people with a mixture of equipment, both new and old. And the question revolved around, should we be backing off on filter efficiency in the winter to improve reliability of operation? And that depends. There's two situations. On-vehicle fuel systems no longer are able to run more open filtration in the winter. High-pressure common rail fuel systems have a very tight filter on them, and they must be maintained in the winter. This is very common practice on older series engines, on unit injectors, to back out from, say, a 7-micron filter to a 10-micron filter in winter to avoid some of the issues of solids generation and allow things to run more easily. Modern high-pressure common rail engines cannot have their efficiency backed off in winter. You will begin to do particle damage to injectors, and that's a very expensive repair. It's different in dispenser situations. You can back off from high-efficiency filtration there to a slightly more open filter. You are allowing some more particulate to move on to equipment, but it will alleviate a little bit of the cold condition transfer of fuels. So for instance, instead of going from a 4-micron beta 2000 filter, going out to just something a little bit more open, 7-micron beta 2000 or so, will allow some of that solids that's generating in the fuel to transfer into a piece of equipment where it will be warmed up and it can go back to liquid. It'll just eliminate some of the headaches. So that's a very critical thing to understand, and different than everyone's sort of historical behavior with fuel and fuel filtration in winter. And lastly, if you would like to connect with us on My Clean Diesel, if you didn't find this webinar from there or you found it on YouTube, there are webinars on there that address almost all of the topics brought up here in more detail. Biodiesel, water behavior specifically, fuel properties, cold flow improver in much more detail. Several of those topics come up in individual webinars if you're looking for more information. Thank you very much for joining, and please connect with us at My Clean Diesel if you already haven't.